As you see, I'm from the date of birth, I'm the youngster here. So I'm less acquainted actually with technical presentations than my elders. Mr. President and members of the Royal Swedish Academy of Sciences, colleagues and guests, ladies and gentlemen, it is a great honor for me to give the Nobel Lecture in Physics for 2002, together with my distinguished colleagues. Today I will focus on subjects on X-ray astronomy which I've been particularly interested and for which I've been recognized. It is a difficult task to talk about X-ray astronomy today because with X-ray techniques we are now studying all known objects of astronomical interest, and therefore focus is particularly required. But I wish to emphasize that hundreds of astronomers all over the world are now using X-ray observations to study all of the subjects in astronomy, from star formation in our own galaxy to the most remote and largest structures in the universe. I'm delighted that some of my closest collaborators have been able to come here today, and their names will recur over and over again in my presentation. And I wish to express to them, and many others not here, my deepest gratitude. The Nobel Prize honors our whole discipline, not me personally only. And now on with the job, which is going to be hard, but I'll try to do my very best. I will start off with a little history to introduce some of the earliest contributors to this field. And certainly we have to mention Herbert Friedman. During the war, the V2 rocket was developed in Germany. Some V2 rockets were captured by the Allied troops, brought to the United States, and first used for scientific research by the Naval Research Laboratory. In some of these rockets, Herbert Friedman and his group put detectors which were the first to detect X-ray radiation from the sun in 1948. And he continued and attempted to look at stars in X-rays, and he didn't see any, and set a limit which was, by today's standards or even by standards then, quite high. It's the same statement about being on top of Everest and saying that the moon is more than 8 feet away. Notwithstanding this very low sensitivity, there was a growing interest which was expressed at the Space Science Board by several astrophysicists about the potential interest in looking for X-ray stars. And I didn't know, of course, anything about it, but I had just joined in 1959 a 28-man private company in which I was then 28 years old, and I was given the job to start space science research in this corporation. The chairman of this corporation was Bruno Rossi, a professor at MIT. He happened to be also chairman of the science board, and he suggested to me that maybe I could look for X-rays from stars. So I started thinking about this, and I must say the first experimental and theoretical review of the field was kind of depressing because it showed that the techniques which had been used to study the sun would probably have to be improved by factors of 1,000,000 in order to have a likelihood to observe stars. And I was lucky enough to come up with the idea of a concentrator that would concentrate X-rays from a large area onto a small detectors. I immediately communicated this to Bruno. Bruno suggested that we put many collimators together, and we published a paper on the first idea about an X-ray telescope. We found out in the literature that Volta had studied this problem, and he also had come up with mathematical computations which showed that you could get a truly image-informing device, just like in any other wavelength. And he was thinking about microscopy, which would have made it almost impossible to build, but for telescopes, which are much bigger, then there was quite a hope that we could do this. So the first thing I want to show you is the estimate to give you an idea of what we thought we were dealing with. The sun, we knew the flux. We asked ourselves what would happen if the sun was at the distance of the nearest star, and the flux which would come out from the nearest, that we would receive at Earth from the nearest star, would be 10 orders of magnitude below the one of the sun. Sirius, if the ratio between visible light and optical was, if they had essentially the same amount of emission in X-rays as in optical, which would have been very strange, because for the sun, X-ray emission is only 1/1,000,000th of what is in the optical. Then we could have seen some more. Again, more than 6 orders of magnitude below. We thought about flare stars, peculiar ray stars, a Crab nebula. We knew that in the Crab nebula there were particles at very high energy, and perhaps if the energy spectrum could be extended, we would see X-rays from synchrotron radiation from these particles. And, but we really didn't know what to guess. And then we thought about the moon, because after all the sun emits X-rays, as Freeman had shown, and therefore there would be fluorescent of X-rays from the moon. And from all we knew, it seemed that this was going to be maybe the largest flux we could see. And so we decided that we would proceed on 2 paths. One was to develop X-ray telescopes, which would have ultimately allowed us to go much below this sensitivity, and therefore extend our observations very far. But in the meanwhile, since the technical development was going to be long, we decided we would proceed with improved detectors, but rudimentarily, and yet 100 or more times more sensitive than what had been previously flown. And I think the fact that most of us had a training in cosmic rays made us look at the problem as a physicist would do. Here are the estimates, here's the instrument I build. I want to build an instrument that can detect the kind of fluxes I'm seeing. One of the things that should be remembered is that the detectors at that time available were Geiger counters. And these Geiger counters, of course, are sensitive to cosmic rays and particles. And these cosmic rays have a flux actually larger than what we expected from the stars. So reduction of the background was an important consideration. Larger area of the detectors than those previously used was an important consideration. And so we went from about 1 square centimeter to 20 square centimeter for each of 3 detectors. And we backed them with anti-coincidence shield, which would remove the background and reduce it by a factor of 10. That's why I said that the sensitivity even of this first, simplest payload was 100 times about better than what had been done previously. I want to recognize that from the experimental point of view, the instrument was really built by Paolini, Gursky, and myself, and they are co-authors of the first paper. In the flight of June, we were surprised. And the reason why we were surprised is because we saw a huge source of radiation, not coming from the moon, a direction away from the moon, but clearly there. This is the summed over many rotation of the rocket, so you sweep the sky, and as it came to this direction, we would see more counts. This is the sum over the entire 305 minutes of flight. We had 3 detectors. One didn't work, so you don't see the trace. One had a very thin window, so you could see X-rays of reasonably low energy. And one had a thicker window, so you only saw X-rays which were harder. And the ratio between these two gave us a rough idea of the spectrum. Now, so there are 2 things, or 3 things to say about this result. First, we find an extrasolar source. I won't go through all of the arguments of why we said it was extrasolar, but one can go through them. Second, the entire sky is filled almost uniformly with X-rays. And we thought and thought about what this could be, and we concluded that they were not associated with our solar system, nor with our galaxy, but they had to be coming from outside the galaxy. Now, the third point that I wish to make is how extraordinary was the existence of this strong source, which was below the level that Friedman could have, or just about at the level on which Friedman had put an upper limit. There was no, although the positional determination was very poor, this is in degrees, this is an entire circle, so we didn't really know where the source was very well. In order to find if this X-ray source, this star, had emitted X-rays in the same ratio as the sun, we would have had to see something, the brightness of the moon there in that position. We obviously saw nothing. So here was a star that was emitting 1,000 times more X-rays than was emitting visible light. There is no known process on Earth that can do that. All X-ray machines put out most of their energy in heat. That's why they have the cooling things, tubes that you see. And so that was 1 point, a 10 to the 9th, 9 orders of magnitude difference in the ratio between the sun output in X-rays and the star. In addition, giving any reasonable estimate of the distance of the star, these stars had to be very, very bright as compared to the sun. 1,000 times brighter than the sun, having invented somehow an X-ray production mechanism different from any we knew on the Earth, was a very strange object. And this finding itself gave a tremendous impetus to X-ray astronomy. There were strange objects in the sky that emitted X-rays at very high fluxes. We could actually see them, and they were very interesting because they presented new physics. So the rest of my talk is going to be, well, I should stay here a moment, is going to be the following. It took about 10 years to understand what this stellar system of Scorpio X1, first X-ray source in the constellation Scorpio, was. And it took almost 40 years to understand what the background was. Now that allows me to hit on, so I have a detective story for you about what the source Scorpio X1 was, and then to try to show you how we solved the problem of the background, I will introduce the X-ray telescope. So the first thing is that there were many flights, many rockets, many groups got involved in the years from 62 to 70, and a dozen or more, 24 sources were discovered. The actual nature of the source remained a mystery, even though, thanks to work done jointly with us by Minoru Oda and Herb Gursky, one of my earliest collaborators, we were able to find the position of Scorpio X1, and an American and Japanese group found an optical counterpart which had the spectrum of an old nova. Now, an old nova, later on, we found out, is a binary system, and so it should have given some hint but there was no evidence from the X-ray emission alone of what this object could be. And so it had to await until the launch of the first X-ray astronomy satellite to find a solution to this problem. And the first X-ray astronomy satellite was a small satellite, about this big. It costed at that time something like $13 million, both to build the satellite and launch it. And I think has been one of the most productive satellites in the history of X-ray astronomy. And it attracted a lot of interest, and both from the theoretical, the results attracted a lot of interest, both from the theoretical and the experimental point of view. I want to recognize here that Harvey Tannenbaum, young as he was, already played a key role in the scientific direction of this satellite construction, which was completely conceived, built, operated by our group. And we were together in Kenya when we launched this. The satellite was a small, was considerably bigger than the rocket payload, but the real tremendous advantage of this satellite were two. One, instead of being up 5 minutes like a rocket is, so it goes above the atmosphere, the satellite stays in orbit for 4 years. So the amount of time available for observation is enormously larger. And second, we had direct control on the speed of rotation of the satellite. So if we wanted to, we could dwell on a particular X-ray source for a considerable amount of time. And this became a key capability to explain the mystery of the SCO-X1-like sources. We would have a rotation every 720 seconds, I believe. And then slowly the angle of the satellite would change with respect to the celestial sphere so that we would scan the entire sky over a period. And by having separate crossing of a particular source, you could determine the location. And by this means, some 300 and some sources were found. And I won't begin to describe any of them. I would just make a few points. Most of the sources are along the plane of our galaxy, which is here represented by the horizontal line. Many of the sources you see, however, are spread all over this map, and it means that they are extra-galactic. And in particular, there was one finding which I will not discuss any further during my talk, but which was very important and it remains very important. And that is the discovery that there was X-ray emission not only from these galactic sources, which we expected, but also from extragalactic objects, the quasars, and more interesting yet, the clusters of galaxies. Clusters of galaxies are ensembles of thousands of galaxies like our own, separated by wide spaces. These wide spaces were thought to be filled with nothing. It turned out that they were filled with very hot gas at millions of degrees temperature, which could only be detected in X-rays because it's too hot to be visible in normal light. Now that's interesting, but the more interesting part is that there is more mass in this hot gas than there is in all of the galaxies put together, in all the parts that we can see in visible light. And therefore this becomes determinant point, the ruling mass, so to speak, in determining the dynamic equilibrium conditions of the clusters. And if we expand this to more recent results, then we now are convinced that most of the matter that is somehow visible to us, whether in X-rays or infrared or radio, consists of hot gas. Now, coming back to SCO-X1, which is represented here, the size of the dot has to do with the intensity of the source, and so you see that's the biggest dot because it was the brightest source. We happen to discover that as we were going across these sources, instead of a kind of triangular pattern that we would expect by these collimation techniques that we had, we were observing variations of the intensity of the source which were larger than what would have been expected statistically. Actually, Minoru Oda, who was visiting our group at the time, was the first to notice that, and we then jumped on it, and the whole group became terribly interested in this. Now, if you see something that is varying, you want to study what it is. I mean, we are talking about sources that were varying their output by factors of 2 or more. It's just as if the sun turned on and off within seconds. And so what we did is we slowed down the satellite, and we went slowly through the source. And the result, without going through all of the agony of the many type attempts, was a very clear pattern of pulsation. The bars are the data, and the fit is with functions, I mean sinusoidal functions. And this was, the source was discovered on May 7, 1971. Ethan Schreier and I worked on it, and Harvey Tannenbaum, of course, worked on a very similar source on which I have less good illustration. So I'm going to be talking about SENEX-3 only as the model for the binary X-ray sources that we study. So first of all, we find this pulsation, and they appeared extremely regular. So regular that we could fit with functions. We could then wait until we would see the source again and phase the pulsation that we were seeing in one pass with the pulsation that we would see in the next pass. And by doing that, we found out that the period, regular as it was changing. And it was changing according to the law shown here. Those points are data points. The error bars are too small to be shown. So what we found was that the pulsation were changing according to sinusoidal laws. We also found, since we had many, many observations, you see here is days, that the source was visible for a certain amount of time and then went away for a certain amount of time. And there was a correspondence between the 0 point of a change of period and the occultation or the maximum visible light. By the way, this is a direct measurement, if you wish, of the orbit of this object, because the reason why the period is changing is because of the Doppler effect. Those of you not too familiar with physics, I mean, it's why you hear the whistle from a train become shorter in pitch than when it goes away. And we are seeing the same in X-rays. The period of the source is made longer when the source is going away from us and shorter when the source is coming to us. The only explanation that makes sense at this point is to say that the source of the X-ray then, here, is in an orbit about a normal star. And this simple model explains all the features of this model, all the features that you saw. Now, the question is, what is that X-ray source, though? I mean, we found that it's rotating around another star, binary system, but what is the source of energy there? Is it like the Crab pulsar, which had been discovered by Hewish and was known to be a pulsating source? And the answer turns out to be no, and a very interesting no. The Crab pulsar is a neutron star. The neutron star is a star which has used up its nuclear fuel, has collapsed, it has sufficient mass to go beyond electron degeneracy and becomes a gas of neutrons to maintain pressure and maintain the star up. But the star of a mass like the sun now would have a 10-kilometer radius, so it's a very compact object in which the density reaches something like 10 to the 15 grams per square centimeter. In water is 1. Now, could it be then just like another pulsar? And the answer is no, because of the following. That in a pulsar, the energy for the production of the electromagnetic radiation comes from the energy of rotation. So the Crab pulsar, which is emitting these pulses, is slowing down. what we found is that our pulsating source was speeding up. So in the process of emitting, the X-rays was acquiring energy, not losing it. So this forced us to another hypothesis, which I think is now absolutely accepted and used in all its derivation, and it is the following. Here is the star, the normal star. Here is the compact object. The gas from the normal star fills this gravitational potential contour line, if you wish. So that means the gas can fall through here, through this nozzle, can fall onto the neutron star. Now, of course, it can't fall directly because, so it has to spiral in and lose angular momentum as it goes in. But basically, the net effect at the end is that gas from this star falls into this very deep potential well, and just like when you throw a coin down a well, it acquires energy because it's falling at the expense of gravity. Now, it turns out that this mechanism, for each proton which you use, gives you somewhere around 100 times more energy than you can get from nuclear fusion. So it is an extremely effective way to produce energy in a cosmic setting. And this was the explanation then that there was a binary system. Gas from the normal star would fall onto a very compact object. This compact object could be a neutron star, or it could be something even more fancy, a black hole. And a black hole, just to make, to make clear that we are not talking about magic here, it's the following. Think of this as a piston that compresses down matter. Normal matter is here, 1 gram per cubic centimeter. In the center of the sun, it's already 100 grams per cubic centimeter. It's much heavier, much denser. When in a white dwarf, Chandrasekhar showed that it would have a mass limit and that the pressure that would keep up the star from imploding was electron degeneracy. When you go even higher density, you push this piston down, you form a neutron star. Electron degeneracy is no longer sufficient to hold the star together, so you transform it into a gas of neutrons. And this is a density which have not yet been reached in the laboratory on Earth, even at the accelerators. But I think that the existence of neutron stars has been clearly proven. We know of no mechanism that can hold up pressure if the mass of the collapsing star is greater than 3.4 solar masses, which was shown by Rhodes and Ruffini, simply on causality arguments. And therefore, we believe, and this I think is a generally accepted model, that for a star which is more massive than this limit, we form an object which is indefinitely collapsing, a black hole. Now, the first evidence we had of such an object existing in our data, so let me just go quickly through. Here is the model now, artist conception. I want to make sure you understand that. Somebody fancied that this is what was happening. Here is the normal star. The gas is falling on the neutron star. The neutron star is magnetized, so the gas can only fall on the poles of the neutron star. And that's why you see the pulsations. This is the model. Actually, this is the model for Hercules X1, the source that Harvey studied more, rather than CERN-X3. We never did have an artist conception of CERN-X3. Now, I want to make a different point. Here is Hercules X1. CERN-X3 will look about the same, regular pulsation over time. Here is a source that doesn't seem to be pulsing at all. And here is Cygnus X1, one of the first sources we saw with Uhuru. And this source pulses, but erratically. The position was found. Harvey Tannenbaum actually noticed a transition. that occur simultaneously in radio and X-rays. The position then could be very much better defined. And Murdin and Bolton in England were able to discover the optical counterpart of this Cygnus X1 source. And it turned out that that optical counterpart gave a measurement for the mass of the compact object of 6 solar masses. So here you have an object whose radius is very, very small, because you can't change the intensity of such an object by factors without involving the entire object. And therefore, that tells us that the radius of this object must be 10 kilometers or so. The mass is 6 solar masses, and we conclude that this is a black hole, meaning that it is an object which, within the current theory of physics, cannot have a stability. There is no way, there is no known physical law that will stabilize this object. Now, the details of how it works, that's a different matter. But the fact that such objects exist, I think, has been clearly established. And here is the artist's conception of Cygnus X1, in which you don't see anything in there. There is no body in there. I mean, there is an event horizon, but there is a disk of accretion, and what you are seeing is the X-rays coming out from the inner edge of this disk. So let me summarize very briefly what the discovery of X-ray binary system implied. First, it implied that there exists binary system composed of a normal star and a collapsed star. Now, to form a neutron star, we believe that we need a supernova explosion. And it was believed that supernova's explosion would disrupt binary system. This was before Taylor found the 2 neutron stars in a binary system. So this proves that that is not true, that the systems stay together. Second, the existence of black holes of stellar mass. We could then, this has become, by now, I'm ashamed of giving you this kind of really tutorial, so to speak, on binary star, but now they become a kind of astrophysical laboratory where we can measure properties of neutron stars very well. The other important point was that here, for the first time, we found out that in the universe, in the cosmos, gravitational infall onto compact object was a very important way to produce energy. And in fact, because it's so efficient. And in fact, this is the model, the only model that we know that works to explain the enormous energy output from the quasars, which I believe are just a scaled-up version, if you wish, of these binary sources. In the center, we believe there is a very massive black hole. Around this center swirl stars, gas, whatever. And from time to time, this black hole eats some of them and produces these stupendous energies that we see in the quasar. So, if you wish, SCO-X1 was such a source, a binary source, and I say we have explained this. Now I'll switch track altogether and try to explain what was the background. But to go through, to do that, I have to give you a little technological introduction, so to speak. And here's the technological introduction. I told you that we had thought about a telescope, and that's a sketch of it. And it works. I mean, why is it so funny? And what are we trying to say? Well, if you try to make X-ray impinge on a surface head-on, they just go through it, or they get absorbed. However, the geometrical properties of conics do not change if you use one piece of the conic of another. And so you could use a piece up here of this parabola. Normal telescope work here, on this side. That's what, Palomar and so forth look like. We work on the extension of this parabola because we are trying to get the X-rays impinge at very shallow angles, less than a degree, from the surface. it turns out, because the index of refraction in matter for X-rays is negative, if you wish, that we have total external reflection, meaning a very effective way to reflect X-rays from surfaces. And so if we make this angle sufficiently shallow, then we can get a very effective X-ray telescope. So that's the idea. That's what we discussed in 1960. It took many, many years and many people's efforts to actually bring this about. I think that I should mention that it was so difficult that, in fact, we decided we couldn't start by studying the stars, that we would try to use these X-ray telescopes on the nearest object, the sun. And Pipo Vaiana, a dear friend of all of us, who unfortunately has passed away, worked mightily in the early 60s and late 60s in going from a kind of a toy-like telescope that we had built and flown on rockets and satellites to study the sun, to this 30-centimeter diameter telescope, already incorporating the idea of nested surfaces, which really wasn't necessary for the sun, but it was a test, if you wish, for the stellar-type X-ray telescopes. He actually succeeded in perfecting very high polish of the surfaces. 1968, we had a real breakthrough. These telescopes now could reach angular resolutions of 5 seconds of arc. One of them was flown on an early space station called Skylab. It was put there, the detector was filmed, the astronauts would come back with their film cassette, we would develop and see it, and we were able to study the sun during an entire rotation of 28 days. And here's a picture of the sun in X-rays as you get it from the X-ray telescope. And as you see, the sun is not a uniform X-ray emitter. This is still poor. Much better picture have actually been obtained by the Japanese in a perfected type of telescopes. But you see the structure of the magnetic field of the sun, which contains this very hot gas, which is emitting the X-rays. So that was the technical development. This is 1973. In 1979, we were able to fly a stellar X-ray telescope satellite. Here's the same mirror. There were different instruments that could rotate on a turret around the axis. And there were star trackers so that we could register the position of stars with respect to our detectors and find position and achieve positional accuracies of seconds of arc. And what did we see with this telescope when we started taking pictures of the sun, of the sky, the night sky? Well, I'll only use one slide to show you these many, many dots. What are they? They are binary sources in the nearest galaxy, our sister twin galaxy, M31. And so now we have extended the sensitivity of our systems by at least 500 times again. And we can study binary sources not in our galaxies that we were doing up to now, but in a nearby galaxy. What objects did Einstein actually study? Many. Essentially, all the objects that you're likely to have heard of on New York Times or other appropriate papers. We could study auroras on Jupiter, planetary studies, X-ray emission from all type of main sequence stars, nova, supernovas, pulsars, and so forth. And finally, groups and clusters of galaxies. Now, I left Harvard in 81. Just before that, Harvey and I wrote a proposal to build a bigger telescope than Einstein, a 1.2 meter telescope. And after I left, he went on and led the effort, which is being brought to successful conclusion. So much of what I'm saying now, I was involved in only as an advisor, or I actually also as an observer. And last year, I was given time to observe for 1 million seconds, which is an enormous amount of time on a satellite which is so much used and so much in demand, but whereby we were able to solve then the problem of this X-ray background. So here is now this monster thing at TRW being integrated. It's called Chandra, after Chandrasekhar. Here is what the thing looks in flight. I mean, I won't spend much time on that. But here is some of the results. I can't resist showing you some of this. Here's the Crab Nebula in X-ray. This is a true live picture in X-ray, in which you're seeing the jets coming out of the Crab Nebula. You see the shock wave. This is a resolution which is better than many optical telescopes on the ground. It's 0.5 arcseconds. You can do better, of course, in optical telescopes if you use adaptive optics, but this is comparable to the very best we can do, except for space telescope up to now. So here we can study the Crab Nebula pulsation. The other one, which is only a week old, is a discovery of two supermassive black holes, only 1.8 arcseconds apart in a nearby galaxy. And nobody seems to be questioning that these are black holes, so we are confidently expecting in several 100 million years that they will collide and produce huge gravitational waves. Right? But this, I just wanted to impress upon you the fact that essentially all objects which are interesting for astrophysics can now be observed in X-rays. Now, what I did in last year with my time is that I stared at one point in the sky for a very long time, more than a week. And where no source was known before, we found some 300 and some sources in about 1/10 of a square degree. That means that over the entire sky, these are all extragalactic sources, over the entire sky, there is hundreds of millions of these sources. And that's why when we had the very coarse resolution which we used in the first rocket, they appear like a continuous uniform background. What are these sources? They are quasars, they are active galactic nuclei containing black holes, producing stupendous amount of energy. And how faint are they and how far are they? They are as far as the more distant objects that we have seen in the sky, at the redshifts of greater than 4. They have optical counterparts which are at the very limit of what the largest Earth and space-bound telescope can see today. In fact, there are sources that we're seeing in X-rays that are too weak to be observed in X-rays, even with VLT, the Very Large Telescope of ESO, or Keck. So this shows you how X-ray astronomy has jumped from seeing SCO X1 to objects which are now more than 9 orders of magnitude weaker than the first source we ever observed. To give you an idea of what that improvement is, it's like going from the naked eye to Keck in 40 years. It took several hundreds of thousands of years to go to make that kind of progress in visible light. So we have moved very fast. Why is it interesting to know this? Well, we have started observing the spectrum in visible light of all of these objects that we have found, and most of them we can measure, and we find that they are at very large distances. We measure the redshift in optical light, but actually they are not uniformly distributed through space. They are distributed in sheets, and these sheets give you an idea of the granularity, if you wish, of the universe, and how the structure may have formed in the universe. So we intend to compare the number of sources we see in these sheets with what we see in visible light, and see if there are differences, if we can, for instance, understand something about the density of the hot gas in the sheets and determine what this difference occurs. And we have seen difference already. I have 2 last slides in summary form. This one is, let me spend a little time on this. This is the number of sources per square degree that you expect to see for any given sensitivity. Here is the sensitivity we had when we found SCOX-1. Uhuru, of course, was much more sensitive. Einstein, which I already described, Rosat, which has been a tremendous success of German astronomy, led by Joachim Tramper and Gunther Hesinger. And finally, Chandra, which has surpassed them all. And this is what we are finding when I said we have several thousand sources per square degree. That comes from our results, this particular plot. Actually, Gunther Hesinger helped me put it together. And shows that there is about 3,000 to 4,000 sources per square degree, which is exactly what we expect. We see 300 in a tenth of square degree. So that's what we see. Now, what are the sources? I already said they are quasars, QSO, but now we are also have the sensitivity to see normal galaxies. And this now can give us another way to study star formation in X-rays rather than visible light and optical. And X-rays has, as usual, a particular approach. It shows the integrated rate of star formation. So there will be all kinds of cosmological studies that can be done with this kind of sensitivity. In plan, there are future missions, at least two, one in Europe, Zeus, which is supposed to be a 5-meter diameter X-ray telescope, assembled on the space station. And the other one, the Constellation program, 4 satellite flying in formation, which is being planned on the American side, and amazingly enough, is going to be led by, was proposed actually, I think, by Javi. So Javi is, I hope he will get his rewards. Now, to summarize at the end, I wanted to use this slide to apologize to all of my colleagues, which I have not named in this discussion. These are all of the satellites that were flown by many groups, and I'll recognize, well, Uhuru, here's the discovery of SCOX-1. As you go down, you become more and more sensitive. This is time in years, okay? So as time in years goes on, we become more and more sensitive. The most sensitive one is AXAF. But XMM is very close by. That's the European project flying right now. Uhuru is here. Ariel was a wonderful contribution by the British astronomers. Akucho, Temma, Ginga from Japan, the group led by Minoru Oda and Yasuo Tanaka. Exosat, a European effort. SAX, an Italian effort. Einstein, again, US and us. Rosat. Astro D, again, a Japanese Extrum, and so forth. And to say that as we go with time, we have gone from seeing X-ray stars, supernova, binaries, clusters, active galactic nuclei, main sequence stars again, normal galaxy, very distant, quasi-periodic object, distant cluster, proto-galaxy, proto-QSOs. So I hope this gives you an idea of the enormous number of people who are contributing to the field now. Again, I apologize. I had to focus. I'm sure it's too long already. And thank you for your attention.